what to expect from you, or what you can expect from me from the class. So may I start with you? Are you a physicist? Or?
No, I am a biologist. I see.
Well, my main subject is philosophy of science. I am studying a bit quantum mechanics, but just so little that I think I cannot say that I know quantum mechanics.
Hello, I'm Christian and I'm a physicist, but I'm doing a master in computer science.
I see. Okay.
Hi everybody, I'm David. I'm a philosopher of language and philosophy of logic. I work with linguistic corpora to analyze political aesthetic debates and dialogues. So I'm interested, I think, more in the second day than in the first day, because I'm interested in computation and quantum logics. Because 2 or 3 years ago, there is a lot of people talking about computation and the power of quantum logics to manage a big amount of data.
I'm a computer scientist with the background from mathematics and logician too. And I had an undergraduate course on quantum mechanics, but I forgot almost everything.
This is a typical history of a computer scientist. You know? I worked with many, and they all tell me the same.
Yeah, I'm a master on quantum computing, so I know some of the quantum mechanics.
So you probably don't more than me in some areas. Okay.
Hi, I'm Nicolas Rossetti. I'm political science, but I'm interested in physics, for mix in the social science and quantum logic.
Okay, thank you. Okay, so this is, I think that this is very diverse. And when I explain some issues on quantum mechanics, I think that you will be bored and the others will be probably not so bored, but struggling getting this. But this is not the first time I experienced such an inhomogeneous audience, and I will try to do my best to comfort you at some point. You know, I think I will frustrate you at many issues, but at least some points might be interesting to you anyway. So let me tell you my background. I started doing high energy physics during my PhD dissertation. I was studying in Heidelberg and Vienna. In Vienna I completed, then I went to Berkeley doing field theory because I got frustrated by ultraviolet divergences and tried to circumvent with thermal correction factors. But as I discovered, this has been already attempted, and they just get you an additional factor, but nothing really that would make you believe that these theories are really finite. But as I later discovered, the problems in field theory may arise due to our formalism, this famous or infamous Feynman diagram formalism you may have heard. And I then went into that, therefore I used these techniques in solid state physics, did some work in Berkeley, and came back to Vienna. Vienna is a city everybody who grew up in or wants to return, you know, so So I have seen many people trying to get away, trying to escape Vienna, but some made it back. And I stayed there, kind of. So and then when I first didn't get a position in academia because it was at that time already very thank you. Not very easy to get one. Now it's much more complicated to set foot in these areas for the younger people, but even at that time. And so I worked for 6 years in the Ministry of Science and Education in Austria, and became a civil servant and always did some physics, and came back then, was able to come back as a professor of physics, and since then happily live ever after as a physicist. I really could have gone into other careers like psychology, psychoanalysis, or even politics, but I regret not a single second I stayed with physics. So and why I'm doing physics? Because I really wanted to, Thomas said that I should mention this, that I really wanted to go to the stars fast, you know, and I wanted to invent methods that would yield these interstellar space travels accessible. So I mean really faster than light, you know. And of course, if you talk in particular to a theoretical physicist, he would immediately say, oh, well, but that causes paradoxes, you know, this infamous grandfather's paradox and all these things. But I believe there will be resolutions of these issues, and finally, physics will enable us to go to the stars in a way that we go to San Pedro de Atacama in a day and come back, or go to the observatories, Alma and Southern Observatory. But not, I don't believe that this will happen in our lifetime. And at least I felt miserably so in this respect. And one cannot pursue all the time. I think this is a strategy to pursue sometimes a strategy of your heart, you know, things that you really love, and sometimes things that you also love, but not so much, you know, so that you have several eggs in a basket. This is, so when one egg doesn't prosper the other eggs, you can hatch the other eggs. And one of these eggs was logic, in particular automaton logic. I discovered a way to model, finite automaton theory in computer science grew out of the effort of a single person, Edward Nummer, to model quantum complementarity. Quantum complementarity could have been imagined long before, because it's just the way systems behave. And there are many systems that behave like that. Once you know that this is that this is the property. But somebody, this Edward Moore in the 50s had this vision, I believe, that just as you catch via the Church-Turing thesis the informal notion of algorithm, formalized it by Turing computer being, just like Turing did the Church in Cluny. He tried to formalize in a deterministic fashion, he tried to formalize complementarity. And it's not in the syllabus, but only shortly mentioned. But if you're interested, I can also talk about this. So I became interested in that and in generalized Ulm models. Almost nobody knows generalized Ulm models, which are very interesting also because they mimic complementarity and many issues that arise, quantum mechanics also arise in these, but they are deterministic or quasi-deterministic. So it's just, I became interested in that, and then of course I had to compare that to the quantum, and I was always interested. In Vienna there are many people working on foundations. Salinger was, at that time I was working with Salinger a lot on foundational issues before I went to Innsbruck, and then he gladly returned to Vienna. This is a long story shortly told, how his return was, and then I started doing work with Pitowski on the Bell-type inequalities, on generalized Bell-type inequalities, and learned to know Specker. Specker was totally frustrated when I contacted him. He says, the quantum community has no understanding what I've been doing, you know, this is true. I have some proofs about this. Now everybody knows, now everybody even claim to measure the Cauchy-Specker theorem, which is funny because I once asked Clifton in '95 how he sees that efforts, and he said, how can you measure a contradiction? You know, the Cauchy-Specker theorem is basically a quite simple construction, and the proof method is proof by contradiction. And the question is how to measure that. The people claim to measure that. I'm a little bit critical, as you might have realized by now, of many claims. You know, it's just not that what they are doing, not the experiments. I think we need much more experiments. I think physics is experimental driven, and also with respect to space travel, we need just more experiments. We need CERN. We need everything we got or are able to get to do the experiments, because I think only this will bring us further. It's the old program of the Aufklärung, you know, of Kant. So, and others, of course, the French, but of course, and the British. I mean, Hume is a hero of mine. I recently discovered Hume, really. So, and there's another thing. There's another local connection. Also with Thomas, I was glad that Thomas took this initiative here to invite me. But I think I was always in the peace movement. You know, this is my political side. When there was this debate with the SS-20, of course the Russians don't have just Steinschleuder. You know, they have really big rockets. I mean, one has to be very careful about this to get a balanced opinion, and I was always trying to get this balance. But of course also the Americans have, as in his famous speech, Eisenhower said, they have these tendencies to deploy more and more weapons, which they produce eagerly. So at some point I'm very pessimistic about the Northern Hemisphere. I attended once a conference organized by Tsichichi. I was a student then, you know, at your age, and I invited myself to this conference. But this is the same. I invited myself to the conference in Brussels also, because I think this was the second time. The first time I invited myself to this conference in Vrije. And the Energy Conference was fabulous in a sense that extremely many famous people who were at that time still living, like Dirac and Wigner, you know, just in Vienna, there was Bennett talking, and says, by the way, this audience, you know, it was packed, the great hall of the Academy, you know, marble everywhere, even false marble, you know, but also real marble. I said, who knows Wigner? And I didn't dare to, because I wasn't even part of that conference, and they hardly let me in. But, you know, they have security now in Vienna. Cyprus conferences. It's amazing. They organized security firm. I strongly resent that. Anyway, so they had this, and they had their reasons for doing this. And anyway, so they, so I was probably the only one who learned to know Wiener. And I also learned to know Teller. Do you know Teller? He was an ardent supporter of the American program to arm. And I was sitting with Teller, Wigner, and Dirac on a lunch table at that conference. And the anecdote that I'm going to tell, and then I'm shutting up. I have other anecdotes which you can ask me in the breaks. Was that Teller, seeing me, leaned forward to me, glanced at me suspiciously, and says, "Are you from Vienna?" And I said, "Oh yes, I'm from Vienna." And then he said, "I tell you only this, my young friend." At this time I was like, "Distrust the Russians." which you need not tell a Viennese, because the Russians were always the big Kontrahenten, you know, on the European War theater. The First World War started because we invaded Serbia and the Russians supported Serbia. Anyway, so I wouldn't go into that. But this was about the topic which is most interesting. It's called the worldwide consequences of nuclear war. Because at that time people were very concerned that these mid-range missiles would make it easy for the Americans to get a first strike capacity, and thus destabilize the European war theater, and thus destabilize the entire world. And there was one message I took with me. They said, there exists a proceeding by World Scientific. And the funny thing is, I was searching this World Scientific proceeding, and they published it under a wrong name. So when I had to referee something, they said you can get some publication, and I said I don't want the money, I want this, but you have to change the name. And it's you can read it. There is a very nice article, nobody realizes that, about Dirac. Dirac had a very simple argument. He said we cannot wage war upon each other because this would be a waste of everything, because if the communists and the capitalists are against each other, you have to read this. And if you cannot recover it from some sites, we all know, you just write, give me an email, and I'll send you the Dirac part. And he said, because if one side prevails, the other side will develop within itself, you know, a new controversy, which will be the same controversy again. So you, from the onset, you don't wage war. It's pure misery to think that and totally incorrect to think that you can solve these things not by peaceful appropriation, but by peaceful measures, but by war. Anyway, the message I took with me was that the South Hemisphere will survive, and you are here sitting on the best place of survival. So if it will come to a meltdown in the Northern Hemisphere, you will survive. And you will have to carry the torch onwards. You know? Europe will be a rubble, and you will struggle, but you will survive, and you have to do, I think you have no choice just to go on and continue what we are doing. So I think there's a strong issue here to get the know-how into Chile in particular. Because Chile, you receive your winds from Antarctica, it's the best place to be. Anyway, so this is my secondary motivation also for doing this. Okay, so let's just start into quantum mechanics. Why I'm talking about quantum mechanics? Because quantum mechanics is the basis of quantum logic. You may know that Planck, in a desperate attempt to explain black-body radiation. This is what I mean when physics is experimental driven. At the Kaiser Wilhelm Institute in Berlin, in the siècle, around 1900 or some years before, they measured black-body radiation, and there was a discrepancy which they could not explain. And of course, it's reasonable to say, well, we just don't know, and we can use the traditional techniques to explain that, and they tried for some time but failed, and then Planck, not really understanding, in my opinion, at that time what he was doing, introduced the so-called light quantum hypothesis, quantized not the energy, not the modes of the electromagnetic field. This is important to realize, because the modes are still continuous in an extended space, but it quantized within the modes the filling factors. The mode can be filled, one mode of electromagnetic radiation, they usually don't tell you this. This is characterized by the polarization and the wavelengths, or the momentum, or the inertia, or the energy. And this can be still continuous in quantum theory of light, quantum optics. But within the node you can have zero photons. So a node is like a box. You might think of the electromagnetic field as a box, many boxes, a continuum of boxes. This is, of course, a contradiction. There is no continuum of boxes because a box basically is discrete. But you might think of that as a continuum of boxes, and each box filled with 0, 1, 2, so with a natural number of those so-called light quants, Lichtquanten, which was one of Einstein's main contribution towards that and towards the experiment. He got his Nobel Prize for the photoelectric effect, not for relativity theory. So this kind of gives you much bigger freedom to create fields, quantum fields, as compared to the classical fields. And they started to understand things. And of course, there was these old theories, classic, what nowadays is called classical mechanics, where they had used vector spaces. They had this notion of phase space, spanned by generalized coordinates and generalized momenta, and these were vector spaces. Now, what is a vector space? A vector space is a space whose elements are vectors, mostly continuous. Now, I think everybody of you has some feeling of what a vector. I hope is. And they used, in particular, Dirac proposed to apply vector spaces to quantum mechanics. So it was really Dirac's idea. It's this famous book of Dirac to formalize quantum mechanics in terms of vector spaces. Before there was this Matrizenmechanik, which basically was also a vector space, but Heidelberg didn't realize that it was. And then, of course, once Dirac has proposed this, the whole machinery of mathematicians sets in. You feed to mathematician something of an idea, and he makes very nice things out of that. there was this anecdote that in Berlin in the 20s, there was a talk about the new quantum mechanics, and Magenau said, I don't tell you at what location, but if you ask me later, I will tell you in private. Said to somebody in the audience, well, Professor Planck looks like somebody, some Russian kulak, you know, who comes after the revolution to Moscow and sees a zebra and says, look what the Bolsheviki has done, have created out of our mules. You know? So they created the whole fancy formalism, and one major contributor to that was von Neumann. And von Neumann was also a hero in quantum logic. Because von Neumann, with his contribution, I mean, he had a famous book, even now famous. Nobody, in fact, I have a colleague in New York who says nobody reads von Neumann. This is so true. Because the English translation is bad and nobody speaks German anymore. You know? But this is one of the few things you have an advantage if your native language is German. That you can read von Neumann and other early books, also Exner, but Exner has partially been translated. Exner is another figure around, you know, this time when quantum mechanics is created. Exner was a famous experimental, let's say he was a physicist in Vienna. I'm not aware, I'm just aware of his theoretical emanations. So Exner became a rector at the University of Vienna and gave a speech that all science, you know, is based on statistics. Of course, he had this idea from Boltzmann and Schweigler. So there was a Harvard philosopher, historian of science, who would call this the Vienna rebellion against determinism. The question was, by the way, what determinism is, and this is classical determinism. It's not really well understood by many people. By the way, I have a recent book with Springer, just 1 year old, which you need not go to those Russian sites to fetch, because the European Union paid 6,000 euro to get it in the public domain. And many things I'm talking about are in that book also. And I did some research on what classical physics amounted to really, and from what I got at least, I mean there are many aspects, but there was this idea, which was a Machian idea, that you have a function. Now a function is something different from a relation insofar as you plug in an input and you get a unique output out of it. You know, this is an old idea, of course. Functions were created that way. So the notion of function is very, very central to the idea of classical determinism. You get a unique input, you get a unique output, and the uniqueness is an issue. Because in classical physics you had these differential equations. And you basically have to ask yourself, when has a function a solution at all, and when is the solution unique? Yeah? So the existence of the solution and the uniqueness is guaranteed by some mathematical criteria, among them differentiability and some Lipschitz condition. So that the first derivative would be bounded, things like that. That guarantees for certain types of differential equations the uniqueness of the solution. And this is really I believe, what is the gist, what should be considered as the gist of classical determinism, that this Lipschitz condition is satisfied with a differential equation. By a differential equation. And let me just talk a little bit more about this classical ideas. Of course, there was this age-old problem, maybe considered theologically or metaphysically. If, as Laplace formulated, there is no need for some mover, who continuously creates events. The theologians, I'm in a John Templeton project and I'm talking to theologians, they would say a creatio continua. There is this creatio ex nihilo, so the universe was created out of nothing by God, and there is this creatio continua, which is an ongoing creation. Out of thin air, God creates instances, occurrences, outcomes, let's say quantum measurements. And they were searching for gaps in this deterministic description, gaps. And if you read Maxwell or most prominently Maxwell, but there are others, some French, which I have forgotten. I would have to go back to the book because I put there all the references such that I can forget them. But they were interesting, extremely interesting French discussion at that point going on. But Maxwell also wrote, he says, but nowadays it's called spontaneous symmetry break. He says, if you have a stone and the stone is positioned on the tip of another stone, which is sharp tip, and you have the ice, and the ice melts in spring, and at some point the stone will fall in one direction, and nobody knows, which direction. So you get, nowadays we would say, because of fluctuations. Anyway, so fluctuations are also an interesting issue. So at that time, they worried about gaps in natural descriptions. There exists another Viennese going to Harvard at that point, Philipp Frank, who wrote a book, Das Naturgesetz, das Kausalgesetz und seine Grenzen, the causal law in its limits, which has been translated, is available via Springer and other sources, and just had a discussion on gaps in the description in classical determinism. And the theologians call this the God of the gaps, God of the gaps. So God does not contradict. There's this notion in the Aufklärung that miracles were always important to mankind. Miracles, in the Roman Empire, the emperors had to perform miracles to stay in power. And of course, there were many miracles in biblical times, and also in the New Testament. There are many miracles recorded. This was a criterion. But these miracles involved things that were mostly against the natural cause of things, natural causation. This is a different miracle thing. They were looking at possible interventions that would, so that the interface would be the gap. And the gap is not determined by the differential equation. So at the gap you don't have a unique functional behavior in time. It's just like the Maxwell example of the stone, Can go this, can go that, it's not unique. There exists a modern equivalent that's called the Norton dome. Have you heard of the Norton dome? Norton is, you know, I think there used to be 2 big centers in North America of philosophy, of analytic philosophy, but I'm totally ignorant probably about that. In this spirit, you know, one is in Pittsburgh, and Norton is head. John Norton is head of the Pittsburgh group. He published this Norton dome thing. You also have so-called weak solutions. Yeah, weak solutions of differential equations, which have no differential functional behavior. You know, it's like the delta function. It cannot be. I mean, it can be differentiated, but only in the distributional sense. You have to use integrals and test functions to formalize these things. So they were discussing, basically, they were discussing these things, whether there exist gaps in nature, and they're still discussing this. But this was already classic. And in modern times, certain similar outcomes in quantum mechanics are like that. So we would postulate that in evangelical terms, you know, there exists now a quantum evangelism. This is not the term I created. This is the term the famous Clauser created. Clauser gave a talk also in Vienna at some workshop, and it's a very interesting article. You could read about the early developments of the experiments relating to Bayesian type inequalities. So he's not Mr. Nobody, but he's the Clauser, you know, the Clauser inequalities, and he was bitter about the reactions of, for instance, Feynman. He said, for instance, at some point he went to Feynman, he had access to Feynman in California, went into his office. Feynman realized that he was going to talk about foundations and measure foundations, and immediately throw him out of the office. So at that time it was not very fashionable to talk about these issues. Coming back to this Vienna debate about randomness, so there were some indications that, from hindsight, that not everything was totally determinate, as even classically. As you can see, for instance, if you read Frank's book on the causal law and its limits, and if you read Maxwell. But Maxwell wrote a lot of things, and it's hidden, you know, it's a hidden treasure in some of his writings. He wrote also very wise things about thermodynamics, but this is to be expected because of his theory of heat and Maxwell Demon and so on and so forth. But he was also into this at some point, and of course everybody mentions Poincaré now with this famous finding that can have very sensitive behavior, predictive behavior on the initial value, that this chaos theory developed out of that kind of thing. So there were some indications, but nothing really in the way that it later developed with respect to quantum mechanics. And I'm mentioning this randomness or indeterminacy because it will be guiding us through many of our thoughts in this course. Not only are there random events, but there are proofs that certain things cannot be consistently arranged in such a way that the parts make a whole. Famous book. Heidelberg, der Teil und das Ganze, the parts and the whole. Because, I think it was Descartes who said, if you want to solve a big problem, just cut it into smaller parts. If you cannot solve the big problem, cut it in so small parts which you can solve, and then solve it coagula, and then make it back again, you know, sub-programs. This is is a famous idea of Descartes. I think in these rules of scientific conduct, I think it's the 5th rule or the 8th. Quantum mechanics sometimes mistakes. I'm going to talk about this related to the Cauchy-Specker and earlier theorems. So, we are again starting from Vienna developing with Dirac's proposal to use vector space as a set of vectors endowed with a scalar product. Now, what is a scalar product? A scalar product essentially allows you to take two vectors and have a linearly or antilinear way of combining them such that you would get a scalar. Yeah, a vector and a scalar. Now, why do you need a scalar? I mean, you cannot. The question is, how can I measure a vector? And the answer, at least as far as I would say immediately, my immediate answer is you cannot. You cannot measure a vector. Now, if you assume that something, as it turns out, the pure state will be formalized as a vector, you have no direct experimental access to the vector. But what you can measure via frequencies is scalars, magnitudes. So you need some instrument, some formal instrument to translate from the vector world to the scalars, and the scalars will turn out to be then the probability amplitude. This is the route to Hilbert space, because the Hilbert space is basically a vector space endowed with a scalar product. Scalar product makes out of two vectors makes a scalar. And the additional requirement that all Cauchy sequences converge. This is the convergence criteria of the old style that nobody so far has managed to make an operational mean out of that. I talked a lot with Seiling and others about we don't need that kind of structure of the Hilbert space at the moment, really. We just need the two other goodies. We need the vector space, and we need the scalar product, but we don't need the completeness. And by the way, this was one of the issues that already turned up with chaos theory. The question is, what kind of formal constructions are, if they are a convenience, yes, and enjoyable, yes, we can conveniently use, for instance, the continuum, the real continuum, as a model of possible places a particle can have, density particle, and then we come back to this age-old Zenon paradoxes. You know, can you make contact an infinite number of, and can you make use of that? So I think Zenon is not, the Eleatic school is up and running and will do so for a longer time. But the question is, do you really need the entire almost transcendental structure of this? You know, the actual infinity is involved. In physics, you have only operational access to the things. And this is what the Viennese physicists hammered into my mind, like Schumacher and Zeilinger, they insisted. You know? And there were, of course, others long before, you know, starting from, from the Greeks, of course, but Hume and there was a famous Nobel laureate, who got his prize for an experimental finding. The experimentalists always insist, but the theoreticians, they like these constructions of the continuum, you know. But we cannot access the continuum. You know? And one famous person emphasizing this was Bridgman, Percy Bridgman. Have you heard of Percy Bridgman? He wrote several books in the programmatic article. A set theory, a physicist's second reaction to Mengenlehre. A physicist's second reaction. He said, probably some of you have long time ago, or some of you working with this all the time, about the Cantor diagonalization. Okay. Set theory, but this has some relevance to physics because it gives you a feeling what kind of entities you use, entities which are totally non-operational. I mean, Cantor created set theory courageously, and I would say for a German professor, amazingly, by defining a set of everything that can be a collection of entities that can be grouped into one, can be thought of. Set doesn't even thought of as one, and this created havoc. All kinds of real structures appeared, like what nowadays called fractals, Menger swarms, Cantor sets, and so on and so forth. Piano curves. So Cantor set theory had two immediate effects. One was that he could cope with certain infinities and could categorize infinities like denumerables and non-denumerables via this famous diagonalization argument proof by contradiction, which was later used by Gödel and Turing in other ways and modes. So here, I mean, he just said, go wild, go wild, young man. He said to those who pursued this theory, because he said everything that can be thought of and then grouped into one. But of course, you know, as all these great things, this was which was too wide. It even known to him already was inconsistent. So it's funny how the mathematicians had coped with inconsistencies, because in 1930, über das Unendliche by David Hilbert wrote, no, this is another thing you can read in German if you want. Niemand wird uns aus dem Paradies vertreiben, das uns Cantor geschaffen hat. Nobody will expel us from the paradise created by Cantor. So Cantor created such a huge world that it was too huge to be consistent. And they are still kind of doing this in the Cantorian spirit. Of course, nowadays they have to say, well, we are using Cervelo-Frankel with the axiom of choice and so on and so forth. But they are basically still going wild in the Cantorian spirit. And the question is, what kind of wildness is acceptable in physics? Because it's an entirely different thing to go wild in the mind, you know, in fantasies. You can have a poetic existence as a mathematician, but the issue is you have to measure it at some point in physics. And this is why I think very wisely nobody listens to you in physics unless you present them an experiment. Yeah. So and this is also at the basis of Hilbert space, because Hilbert space consists of a continuum of vectors, almost in an exact sense with Lebesgue measure 0 are computable. You know, computable in the Church-Turing sense. So almost all of these elements are incomputable, and inaccessible in physics. And then you can say, well, we are using this because out of convenience. They are every Cauchy sequence converges or whatever. I'm not talking about in the theoretical style. This gave much confusion. It gives sometimes much confusion because some people come up with weird mathematical consequences of the fact that we use the continuum. Yeah. So, for instance, Pitofsky, this was an ingenious way, used paradoxical set. This is how Pitofsky started. He wrote a Discrete letter in the early 80s saying we can use paradoxical set decompositions to explain the non-classical probabilities of quantum mechanics. Using this famous Banach-Tarski paradox. And or there was this other person, this other researcher, saying that he has nullified the Cauchy-Specker theorem by just using a different set than the continuum, the classical continuum for vectors. There's another anecdote. I have to admit that I seldom read every single issue of Hilbert letters. So at some point, Specker, who I knew very well, he was at that time, called me up in Vienna and said, "Karl, you have to write something. Somebody has just published a paper on nullification of the Cauchy-Specker theorem. Does anybody know this Meyer paper?" I was unaware of it, so I had to come back and discuss. And she says, Specker says, this is part of my frustration. They don't understand this. They just go wild with this formalism. It was a kind of retranslation, the paper of finding by Docent and Sachs that you can have three colorability of the sphere with such that three colors are always, if there's a tripod, an orthogonal tripod, you can have, the points of the sphere, you have the vectors from the origin pointing outwards, and you have the unit sphere, and you just consider the points touching from the vector touching the unit sphere. And there exist always triples, of course, which characterize the orthogonality. Yeah. So when three mutual orthogonal vectors in 3D stretch outside and touch the unit sphere, you get 3 points. And Docent and Sachs proved that you could three color them if you assume that only Pythagorean triples are involved. Now, what is a Pythagorean triple? The Pythagorean triple is easy. It's if you know that a squared plus b squared equals c squared, the Pythagorean triple would be 1 over a, 1 over b, 1 over c. And you take all, you can prove that there exists an infinity of such triples and they are dense on the sphere, you can prove that. And they have a result where they prove three colorability. And if you identify two colors, you basically get a coloring scheme of the unit sphere, which contradicts with the Cauchy-Specker theorem, because the Cauchy-Specker theorem says you cannot do this two coloring with these rules. Of course, this is very restrictive. It's the numeral. It's the numeral, and it's not continuous. There was a funny twist to that. On Specker's suggestion, I discussed things with Specker. We pulled with a geometer, student, and sent this as a comment to physicist letters. And the referee says this is a perverse paper, and they don't understand the gist of the Cauchy-Specker argument. And that's funny because it was coordinated with Specker. but this happens sometimes empirically, you know, in physics. So it was published elsewhere anyway. But I mean, these kind of experiences, if you allow me, in physics take place. Now, okay, so be aware that the introduction of the Hilbert space introduces a non-constructive element into the theory, but usually we are not really concerned about that. Only such extreme situations, exotic proposals, I would call it, these things turn up. So once Dirac proposed the vector space formalism, von Neumann published his book and a lot of papers on Hilbert space formalization of quantum mechanics, and I'm always talking about this Hilbert space formulation of quantum mechanics of von Neumann, really of Dirac von Neumann, when I'm as long as I let me talk this today and tomorrow. And later, after his book, when he was already in the United States, von Neumann pulled with Birkhoff, who was a lattice theorist, and algebraist, pulled his know-how together, and they produced the founding paper of quantum logic. So basically, what quantum logic was about is they identified certain entities in Hilbert space and identified with logical entities. What are logical entities? Well, the basic logical entity is a proposition, true, false in classical physics, and operations and relations. And that's how quantum logic started, basically. Then there were several attempts to augment it. For instance, Koch and Specker produced a series of papers nobody reads. The final paper was this thing everybody cites but nobody reads. I can give you an anecdote, but not in public, about this. Anyway, so and that's how things developed historically. And this is a motivation for you to continue listening to me, because now it's going to be strenuous. Because at some point I have to at least give you some idea of the formalism. Yeah? But this is how I think we still are now. We are still now in the process of figuring out what consequences this formalism invented by Dirac and von Neumann, also Birkhoff and others, and motivated by those experimental findings which were then used by Planck and Einstein, and of course Schrödinger, the spectrum of the hydrogen atom. And in many body physics, there is field theory with this development of the von Neumann theories, which are divergent. So we are still contemplating the consequences of these things. And the interesting thing is that all the consequences we have derived so far are in perfect accordance, our predictions from these formalisms are in perfect accordance with what we actually measure. We have not found a single instance, not an edge of a, everybody would be happy, to find something which is a contradiction to the formalism, to the quantum formalism, but so far nothing, nada. I think it's in Spain. Yeah? Nothing. So this is sadly for many people because it's, it means if there's a contradiction, you have to go to you're free to speculate, But in a sense, it's also interesting because this formalism of vector space. I have 10 minutes. So this formalism of vector space has been with us for 100 years almost now. Not entirely, but almost, and it has produced a pandemonium of things. Some people used to sell to you as kind of new age. When I came to Berkeley, first thing I saw was a full pigeon box of letters. So this guy received more letters than the entire rest of the department. Do you know who was that? It was Vrije Capra, the Tao of physics. And he was a visiting scholar there, and he has published the Tao of physics. And I mean, this is extreme, That, I mean, you could easily say that, well, this is just speculative, and he tries to do things, but also this vector space formalism serves sometimes almost as a evangelical way of seeing the world, which is unjustified by the experiments. So I tend to have a rather down-to-earth approach, trying to see, what's really going on, and not to see what you would wish it to see. That's what Sigmund Freud, coming from the town of psychoanalysis, and this is also my personal history, a little bit, Freud said, you should, if you have a client, and in this case, nature is our client. In the theories we have. If you have a client, you have to be very cautious as an analyst, not to take your private projections onto the explanation of what's happening within this client. So you shouldn't project too much. And later on, totally independent. I mean, this is an age-old advice, of course. Freud wasn't the first one and the only one who said that. And later also James said this. He called this the mind projection fallacy. James was not very satisfied with the way the quantum formalism was presented. He said that many people have their own program, their own little desires to make out of quantum formalism something of an evangelical theology, which I would rather refuse. I think the main point is that you have to see it as a historic effort to know more of the world. And it's embedded in history, as Danny Grimberger says, very concretely. He once said, in 400 years from now, people will consider what we do ridiculous, as we might say. They might not, I would say, probably not ridiculous. Danny was a little bit overstating these things, but you have to see it as a stream, as a flow, as a historic flow of ideas and things that developed to make sense of the world and to manipulate the world, also industrially and technologically, which is extremely so far successful. But you have to see it as a historic effort, and as a historic effort, it gets not an ontologic touch, but an epistemic one. It's the way you see it, not the way it is. Of course, you know, for the physicists, it's always for them, they said that for all practical purposes, you have to think that it is. You have physicists are ontologists by nature. And they don't like to put their nose to the epistemology of the things. But of course, if you look further away from a further distance, you have. I'm not preaching idealistic philosophy here, but in a certain sense, everything is. There has been recently a book on idealism by Oxford University Press, and the editors whom I learned to know, who are the most interesting guys I've known from Oxford, they published a saying saying the world is thought through and through. So also quantum mechanics is part of this through and through world, and is a production of our thoughts, and a very successful way of doing predictions and doing technology, and but shouldn't be taken as the truth, you know, because it's just us that are thinking about this world, and so quantum mechanics is in a sense extremely successful, and at the same time we should be looking ahead of it. What comes next? There will be a next. It would be totally ahistoric to think that there will not be a next. Of course, the contemporaries always tell you that there is no next, because it's very difficult to bear the notion that you don't know the truth, if there is a truth. Anyway, so with these remarks, I would close my first introductory part, and I will then go now a little bit into the formalism of quantum mechanics. Next.